Since the Cold War, competition among space organizations has mostly withered away. NASA ended up developing the space shuttle, which wasn't too successful, and Russia decided to just use Soyuz for the next 50 years. Meanwhile, a handful of private space companies have sprung up over the past 2 decades, and though there has been fierce competition amongst them for commercial contracts and reusing rockets, recently SpaceX has pulled ahead of the crowd by quite a bit. Right now, it would seem like SpaceX has a clear shot at placing humans on Mars first. But through all of this, most of us have completely overlooked China, the only other country capable of launching humans into space. So here's why China could beat Elon Musk to Mars. Well, starting off, China is extremely secretive about their space program, as they don't want the competition to know what they're doing nor how they're doing it. So, we don't have very many clues as to what rockets they're developing, how they plan to handle the various challenges of getting to Mars, or anything like that. But what we do know is that China is making significant progress in the realm of space. If you don't believe me, just take a look at the type of tasks that we know that China is working on. In 2011, China was banned from using the International Space Station due to national security concerns. Instead of becoming more transparent and working with the US on the space station, China was like, alright, that's okay, we'll just build our own. They didn't even hesitate. They simply went ahead and launched Tiangong 1, which is a single module space station, into space the very same year. This space station would stay in space all the way till April of 2018. In the meantime, China would launch Tiangong 2 in September of 2016, and this station would stay in space till July of 2019. To top it all off, China is currently working on launching a massive space station into space through 11 launches over the next 2 years. Aside from this, China's Mars rover, Tianwen-1, just recently entered orbit around Mars, and they are planning a landing between May and June. If they are able to successfully land this rover on Mars, this would mean that China actually beat Russia in landing a rover on Mars. Clearly, China is not playing around, and this applies to sending a crew to Mars as well. China has not revealed a specific year in which they want to get to Mars. However, they have given a broad estimate stating that they want a manned lunar base and the capability to send humans to Mars by 2045. Now, that's quite a bit different from Elon's vision of getting to Mars by the end of this decade. But one thing to keep in mind is that the deadlines China puts out are taken extremely seriously. I'm not saying that Elon's deadlines aren't taken seriously by SpaceX, but the deadlines he puts out are more of an ambitious goal meant to push forward the team as opposed to an actual drop-dead date. After all, the crewed Mars mission has been delayed from 2020 to 2022 to 2024 to 2026 now. And though they are making outstanding progress, I have a feeling this may be pushed back a few more times. With China on the other hand, the dates they put out are drop-dead dates, and they have a pretty solid track history of keeping to those dates. For instance, in 2016, they announced that they were launching a Mars rover in 2020, and they did. Later on, they announced that they were launching a permanent space station in 2021, and it looks like this is about to come true as well. Considering this, I think it's quite likely that China sticks to the 2045 deadline. Also, keep in mind that that's a broad deadline, including both the lunar base and crewed Mars mission capability. It's quite likely that the internal deadline for a crewed Mars mission is somewhere in the 2030s, which may allow China to beat SpaceX to Mars. This really isn't surprising, as China has been trying to flex their powers in every single way possible, whether that be their economy, their military, or their space technology. However, unlike their other endeavors, China has yet to really make their mark in space. This isn't to say that China hasn't accomplished outstanding feats in space, but none of their feats has really attracted the attention of the average person, because they have yet to be the first at any major task. They weren't the first to reach space or the moon, and they weren't the first to launch crewed missions. China was actually the first to land on the far side of the moon, but the average person doesn't really know and frankly doesn't really care about that. However, something that everyone around the world would care about is the first country to reach Mars. As a result, I'm quite sure that China is at least trying to claim this title, even though they haven't announced it publicly. With that being said, let's take a look at some of the reasons why China's National Space Administration, or the CNSA, is well positioned to actually accomplish this task, starting with the national pride. The US and Russia are already known for their leading space technology, and they don't really have to prove themselves, except against flat earthers and moon landing conspiracists. Meanwhile, China is generally grouped into the second tier of space organizations, with India and Europe. Considering that China is trying to prove themselves as a world power, national pride will no doubt push forward their progress to Mars. Another major benefit for the CNSA is the fact that it's a government organization. This is quite ironic, as in the US, NASA being run by the government is actually a major setback. New presidents and congressmen switch around NASA's plans all the time, making it extremely difficult for them to make any real progress. With China, on the other hand, we have the Communist Party. Though this may be quite annoying in other sectors of life, it's quite useful when forming a central national goal like reaching Mars. I read a comment about NASA a couple of days ago, and it's absolutely true. If NASA scientists determine that switching to stainless steel is the move, they have to go through a lengthy approval process. While the decision is passing through Congress, we'll probably see some random congressman whose districts rely on carbon mining or something vigorously oppose the switch. With the CNSA, though, like private space organizations, if it's better, it's better. There's no external factors hindering or influencing the decision. Aside from having the freedom to make centralized long-term goals, the CNSA also gets massive funding with no strings attached. NASA has to answer to the US people, SpaceX has to answer to their investors, but the CNSA only has to answer to the CCP. I'm not saying that the CNSA can just do whatever they want without consequences. Rather, the CNSA doesn't have to put together press releases and conduct shareholder meetings and raise funding or anything like that. For the most part, the CCP gives them $11 billion and tells them what to do, and the CNSA just does it in the best way possible. To put that in perspective, SpaceX only received $2 billion in revenue throughout 2019. This means that the CNSA enjoys similar levels of freedom to SpaceX, if not more, and they get over 5 times the funding. Moving on, China is also quite a bit ahead of SpaceX at this point in time. SpaceX just reached the International Space Station last year. Meanwhile, China is literally working on launching their own massive space station. On top of this, they have completed missions to the Moon and potentially Mars very soon. As a result, they actually have the advantage in terms of technology and experience right now. It should be noted though that they aren't nearly as innovative as SpaceX, as they don't have self-landing boosters or belly-flopping starships. But technically, you don't really need reusable rockets to actually get to Mars in the first place. Reusable rockets are really more for the long term as they allow for sustained cheap space travel. So, it's possible that China simply brute forces their way to Mars in order to claim the title. And that brings me on to the final major reason that China could beat Elon Musk to Mars, which is that they are not ashamed of copying what works. Copying happens all over the place, from the smartphone industry to the automotive industry, so it's not really surprising. But unlike most companies, the Chinese often don't even try to hide it. For instance, take a look at their Long March 2C rocket. Aside from looking similar to the Falcon 9 at first glance, if you look closely, you can see that the grid fins of the rocket are basically identical to the Falcon 9. There are even some rumors suggesting that China is already copying Starship behind closed doors, which is quite possible. I'm not quite sure if they would directly rip off Starship, but I wouldn't be surprised if
I don't know what's wrong with that.
of their rocket. Combine this with everything we've already discussed and China's super fast manufacturing process, and you can see why it's not that unreasonable for the Chinese to be the first to Mars. At the end of the day, I still think SpaceX will be the first to Mars, and I am rooting for Elon Musk. However, China has been making massive progress in terms of space technology, and considering the
The old space station.
their drive to prove the superiority of China, and their willingness to copy, it's very possible that even if they are not the first to put people on the Mars, they will be the second. What do you guys think about the CNSA? Comment that down below. Also, drop a like if you guys want SpaceX to get to Mars first. And of course, consider joining our Discord community to suggest future video ideas, and consider subscribing to see more questions logically answered.
Interesting.
Again, I'm Hari, and I'll see you guys on the next one.
I like this guy's branding. Logically answered. The old LA, but the L is like part of the A. I like it. Okay. So, today we're going to do a little break from the thesis, and I'm actually going to work on an assignment that's due this week. It's a pretty big one, it's 40%. That's why I'm kind of taking a break from the thesis. Also, it's nice to mix things up, I guess. So let's get the document running. Alright, so what am I up to? Electronic subsystems coursework. So this is all about monitoring appliances on a spacecraft. So I don't want to capitalize that. Okay, so first we're going to do a diagram, which is what you can see up here. This is like applying in all the monitors, showing where all the monitors are. As well, I want this to stop moving. Okay. Diagram showing where all the monitors are, as well as a legend clearly describing the diagram. Okay. 2. Introduction, where we discuss monitoring, why it's important in general terms, etc. As well, in the introduction, brief description of each monitor, as well as statement as to what its output is. So instead of having to say, okay, for a solar array we measure temperature, we do that with a thermometer. For this we measure temperature, we do it with a thermometer. Instead, we just at the beginning say a thermometer measures temperature, and then that way we don't have to repeat it over. And finally, go through each subsystem and describe its monitoring. That's essentially it. Okay, let me turn on my music. Okay. So these like pinky orange boxes are voltages, are voltmeters. So you have one box here and one box here. You detect the voltage here and the voltage here, and then you're able to get the difference, which is like the voltage going through the system. You do it for each component, or each like kind of junction in the wiring system. And you have the same happening over here and here. Now, as far as I'm aware, in this assignment, we don't really care about this stuff. We care about 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So we talk about the solar arrays, the controllers, the shunt, the battery, and the regulators. So we'll be describing what each of them do. We'll be describing what instruments used to monitor them, and what that output will be and why that's useful. So the only monitors that we care about are voltmeters, thermometers, and switch. I think switch regulators they might be called. So like right here you have like a little switch. As you can see at the moment it's off, but like if that line joins in here, then it's on. So that's like the notation in electronics for a switch. So we'll have a component here that monitors if that switch is on or off, like a binary system. It will return a 1 if it's on and 0 if it's off, something like that. So we can put those in now. So like a triangle. Okay. We are going to do no fill. We'll make it a little bit thicker as well. Okay, there we go. And we'll keep it that dark blue color, and we'll just copy it, paste, and get another one. Like that. Copy and paste. You gotta be careful when you're doing this on PowerPoint, just because it doesn't know sometimes if you want to move the picture that's on or the shape that you're trying to move. So you have to be very careful with your mouse. So like that. We'll do another one. Oh, is it just 3 switches I can see there? I think it is. Just these 3, so I don't think we need another one. That's all. They're all the switches in the system, I'm pretty sure. Okay, and finally, the thermometer, which is super important. You want to make sure all of your stuff is not getting too hot, because heat tends to be like the biggest failure in these systems. So you want a good way to dissipate that heat. So first off, let me get rid of this triangle. Cut. Alright, see you, pal. Okay, so what do we want to know the temperature of? Definitely the solar arrays, because I think if you know the temperature of those, you get a good estimate as to what your output from that will be. So before these missions take place, they tend to know, okay, we need like X amount of energy that's produced from these solar arrays. So by having a thermometer on them, you can see what the average temperature of them are, and you can then infer, okay, if it's above this average temperature, then the mission will go for the time we foresee it to go for. If not, we need to either adjust the position of our solar arrays, or something's not happening, or like there might be something broken, you know. So we'll definitely have them going across all the solar arrays. So let's just put that in now. So we'll do like a red circle, red for heat, red for hot. I'll make it a bit bigger. Okay, no fill. Outline will be 3x, and we'll use a nice red color. Okay, so same as before, copy and paste and move over. Maybe it's a little bit too big. Make it a bit smaller. Okay. And this one, I can just delete that, I guess. Cut it out. And I can just copy and paste this one exactly. So copy paste, move over. Copy paste, move over. Copy paste, move over. Okay. What else? The battery, 100 million %. That's definitely going to be measuring. We're definitely going to be measuring the temperature of that. The battery is, so the solar arrays feed energy into the battery. The battery takes that energy and then feeds stuff out then to, let's say, the communications, your thermal energy, your propulsion, and then your scientific instruments. If that overheats, then there's risk of, like, some of your instruments might get too much energy, too much power. It might overheat so much that it actually breaks and nothing gets power. So monitoring the temperature of your battery is very important. So we're definitely going to be putting a big red circle in there. So copy and paste. Like this. And we'll make it nice and wide. Ooh. Perfect. I feel like we should probably have a thermometer on the shunt as well. So I'm just gonna, I'm gonna do that. Copy paste. Something like that. I think that's the diagram. So we're checking the voltage across these systems here. We're checking the temperature of each of the solar arrays, and we're checking to see if all these switches are either on or off. Now, one thing I'm not 100% sure on, and I'll have to look into some literature on this, is I feel like the switch monitors might be a little bit redundant, because I feel like if you're getting a response through the voltmeter, that should in itself tell you if it's on or off, like which is what the switch will do. Now, the only thing I can think of is it's more like a reliability thing. So I don't know, let's say this voltmeter breaks, then you don't even know if it's on or off, let alone like how it's performing. So having the basic knowledge of it being on or off is like important So if you do see the voltmeter is broken, you know how to go about fixing the solution. It's like a troubleshooting thing, I guess. Now, the next issue is then, if you have a spacecraft that's, let's say, I don't know, monitoring the sun and checking out, like, I don't know, solar wind parameters, let's say, it's very far away, right? So it can only send back so much data, and you want to try and prioritize as much of that data as possible as scientific data, so you can learn things, right? You don't really want too much monitoring going on. Only enough that, like, if something goes wrong, you know how to fix it. Like, so the issue is, are we monitoring too many things then as a result? And as a result, then we're not able to send back as much information as we would like. So it's a big trade-off. It's how reliable do you want it to be, versus how much data you want to get back to make new conclusions and learn new stuff, right? So it's a fine balance you have to tread, really. But yeah, I'm pretty happy with this diagram. I guess I can do the legend down here, which I'll do now. So can bring down. Okay, and the kind of pinkish orange box. I gotta be very careful about moving around the picture, because all my instruments will be off. And then the final one is the switch monitor. Okay, perfect. So now we'll put in some text boxes. Insert text. Yeah, there we go, text. Okay. Can I copy and paste this box? Okay. So for this, we'll say, let me just get the coursework sheet up so I can see exactly what the wording is. Bum 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 bum. Okay, hang on a sec. Okay, so it's called a temperature monitor, a voltage monitor, and a switch monitor. Simple as. Okay, so let's just say it as is. I think that's perfect. I don't think anything else needs to be put in here. The only thing is, I wonder if I have my monitors correctly placed. So, like, one argument is maybe could you have like one thermometer or one temperature monitor for the whole solar array? I think I like having individual ones because I think having knowledge as to what the temperature of each one is quite important. For example, like let's say if number 2, 3, and 4 are all pointed towards the sun, and number 1 is pointed away from the sun. If you only have one temperature monitor across the whole 4 arrays, you'll get a result back that is less than you think. But you don't know, with the information you have, you don't really know what to change to increase that average. You know that you have to point an array towards the sun. You know that probably one array isn't pointed towards the sun. But if you don't have individual temperature monitors, how do you know which one is underperforming? You don't. So yeah, that's the main issue, especially on like a smaller spacecraft where you'll know that each array will probably be at different locations of the spacecraft. So they won't necessarily all be like on the same side pointing the same way. In which case you could only have you can just go for one, because you know that if it's underperforming, they're all underperforming because they're all pointed towards the sun. So that's something I can talk about in the report. Depending on where the solar arrays are positioned on the spacecraft, you can kind of either have one big thermometer or like a load of smaller ones. The switches I've talked about already. We can get into that in the report as well. The voltmeters. Again, for a similar reason, this is even more important than having just one big voltmeter. If you have one big one and you see your system is underperforming, again, you don't know which one is at fault. You don't know how to change or fix it. Whereas if you have individual ones, you know which one is fucked up when you just read it. Like, okay, like let's say 2, 3, 4. You see 2, 3, and 4 are all giving back thermometers or voltages that you'd expect, but one is like 0. Then you know either the switch is off or it's broken. Whereas if you have one big one, then you have an average that you know is smaller, but again, you don't know what to fix or what to change in order to get that average up. Battery we've talked about already. I'll probably go into a bit of literature for that just to see, I don't know, like examples of battery overheating like being a detrimental aspect of a mission, let's say. And then yeah, voltmeters here just to make sure all of these instruments are working too. But we don't care about these. We're not going to worry about these. Okay, perfect. Diagram finished. So I'm going to snipping tool this just in case I like lose the PowerPoint or something. And we'll move on to the main report. Okay, save that. Okay, so what will I put on the main screen now? I could put the task brief maybe. Okay. So what's going on here? So these are the 8 systems that we care about. So we have the dissipative shunt, which gives us a bit of power, as well as the battery here. And then the regulators and all of these are actually the individual instruments. So I might just check Moodle and see if there's any relevant lecture slides I can look up as well. Did not go to this lecture too much, unfortunately. Okay, we have something on power and regulation, batteries, regulators. This looks promising. Altitude sensing, don't think that's important. Reliability could be important, so let's get that out. Mechanisms and housekeeping for sure. So we'll get those 2 coming as well. Harness and EMC, no, don't care about that. That's for how like electromagnetic waves impact our appliances. Okay, cool. I think I have all the relevant slides I need to look at. So first of all, I'm gonna kind of put stuff in folders. So first off, I have a couple of ESA slides to look at. Let's get through these very quickly, just to see if there's anything interesting here I can include from my report. Alright, what's going on here? Is it long? No, it's not. It's like, what, 20 slides? It's fine. Alright, let's get a pen and paper out. Okay, what's going on here? The availability of competitive solar cells and solar arrays is necessary for scientific Earth observation missions. Yep. High efficiency, power to mass, power to cost, power to volume ratio. Okay, so maybe we assume that we're using wing arrays. Oh, if we're using wing arrays. Okay. Oh, I should just fucking. I'm just gonna type this down actually. Quicker. Let's put that up here. Okay, so GA. Well, first of all, this is the 2015 solar slides. GAAS, much greater than silicon solar arrays. So you don't really care exactly how the solar sort of works. We more care how we measure its performance. Yeah, this paper is just kind of talking, or well, these slides talking way too much about like what a solar cell is and how it works and what the developments are in that front. But like as I was saying, I just wanted to look at stuff to do with measuring the output. I don't really care about what the output is. Just all I care about is safety in this report. So there wasn't anything interesting here for me in that regard. Alright, what else do we have here? Okay, let's check this out. A proposed work plan, okay. Okay, let's just get through this. Okay. All I care about is safety. Maybe for deorbiting technologies, that's pretty important for safety, so I could see a little bit of that in there maybe. Okay, so they're talking about like safety for crash landing, is it? Yeah, I don't care about that. Okay, yeah, so it's talking about for at the end of life of a spacecraft how to kind of make sure it kind of defunctions in a safe way. But I don't mind, I don't care. Keep going. Hello. How are you, buddy? I hope you're not going to debate me on maths. I'm a little bit tired today. Oh, photonics. There could be something interesting here. I'm just like kind of skimming through this and I can't see anything interesting. Let's keep going. If I control F monitor. Okay, 6 results. Okay, so they don't really talk about why we monitor stuff, they just like assume the reader knows it's important. Yeah. Okay, so nothing interesting here. Okay, did I open up another document? I thought I had 3. Okay, let's check the slides. No. Okay, let's check reliability. Bum 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 bum. That's 7. Ooh, the capacitors are interesting. I don't think I put anything on my capacitor. Might have to go back and fix that. Question is, do I put a voltage meter or a temperature meter? Probably a voltage meter. Maybe you can infer from the temperature of other instruments what the temperature of the capacitor will end up being. Okay, interesting. Ooh, so do I know what mission I'm on actually? Do I know? Let's see. So it's a science mission lasting many years. It doesn't say what type of science mission it is. I don't think it would have been that helpful anyway, regardless, but fuck it. Keep going. So we have both of these. Okay, so let me put that in the notes. This is lecture 2. Okay. Solar cell temperature variation. Discussing the various, I don't know, operations such as Leo, mounted cells on paddles, etc., and the expected variations. That's slide 12. Okay. I mean, it didn't say in the report what type of ray it is, so I don't think this is too important to look at, to be honest. Let me just check one more time. Blah 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 blah. Science mission lasting many years. Blah blah blah. Yeah, it doesn't suggest any type of specific array. So doesn't matter. This stuff doesn't matter. Um, keep scrolling. Power regulations could be cool, but maybe not. Ooh, interesting. They use a voltage control. Okay. When the overall power requirements of a spacecraft rise above the limit set by the maximum power The shunt regulator can dissipate. Oh, and then it's saying the next things, yeah. Interesting. Okay, these slides are actually pretty cool. I think that this one is very relevant because it has the two type of controllers. I just want to look at this one more time. Next one. Back in 1 sec. Ooh, okay. Let's have a look at this. Do you know what? I think I'm gonna just get started writing. Yeah, I just want to get started writing, and then when I come into problems, I can just check out my notes and see what the story is. I never understood electrical circuits. Yeah, I mean, I don't fully understand them either, to be honest. They're a bit weird. Like, notation-wise, like, this is a resistor. This triangle. Oh, I forget what the name of that is again. Yeah, I mean, these little things are resistors. I don't really look at the diagram as much as I should. I just kind of read the words and see what's happening in it and just kind of work off that. But again, maybe that's why I find it difficult, you know. I actually might just type directly into overleaf, just so I can have something on the screen. Bum bum bum, bum bum bum, bum bum bum. Okay. So let's go in here. In Spacecraft, the scientific. Okay. Monitoring the spacecraft's. So first of all, apostrophe here. Monitoring the spacecraft subsystems is a potent way to efficiently identify and eliminate any areas, I guess, in the operation of. Is that University College London? Yes, it is. This is like an overleaf document, so this isn't like anything specifically from college. This is literally just a document I made on overleaf. With like a header of UCL and stuff, just for like when I had in reports, just so it kind of looks nice. So nothing too crazy here. I misspelled this. Operation instead. Okay. Monitoring the spacecraft subsystem is a potent way to efficiently identify and eliminate any errors in the operation of the spacecraft. Okay. Heat regulation, yeah. Like thermal errors tend to be the biggest kind of breaking point of any electrical component, like not even just in space. And the issue when it's specifically in space is that it's very difficult to fix something when it's broken, because you can't get someone like to go up and fix a spacecraft that's orbiting the sun, right? So instead, what tends to happen is you have like, I think I might have my diagram still here. Yeah, I do. So this is like an example block diagram of like a spacecraft. And you have these 4 solar arrays here. And all of these are getting energy off the sun in the form of light, and then transforming it to heat energy and then electrical energy in the battery. And that runs all of these. So all your instruments and your propulsion is all working. Just don't design something broken. The thing is, you want to design something that if it breaks, you have an easy way to stop that problem becoming a bigger problem. And that is done here, let's say in a solar array. Instead of just having one solar array, you have 4 smaller ones that when added together equal the same initial solar array you would have made in the first place. And you have this switch here, right? So let's say solar array 2, 3, and 4 are all fine, working well. But then solar array 1, it's overheating. It's like, I don't know, something's happened, it's getting too hot, and there's a risk of the whole spacecraft blowing up because of that. What you can do is you can just turn off this switch, and based on your monitoring data on the voltmeters and the temperature monitor here, you can then try and figure out, okay, why is this overheating? Are we pointing it in an incorrect way? Is the way we're pointing it, is it now too close to, let's say, the shunt regulator, or is it too close to the battery, so that the excess heat from these components are getting onto the solar array, excuse me. So the switch is designed to stop it in its tracks to figure out how we can fix it, and then it can be turned back on again and see what happens. So that's what you do. You design them in such a way that if something bad happens, you have a easy way, not an easy way, you have a kind of efficient way to just fix it. Yeah. Okay. So where was I? I have my document here. Yeah, okay. I was just doing like a quick intro. I'm just gonna get chat on my phone just because I like having my 2 monitors working away. Okay. Okay, I selection. Why did I have selection here? A spacecraft launch is a very expensive endeavor. As a result, in practical terms, it is very important to ensure you are not overpacking your spacecraft. Ideally, you would have just the instruments on board which can provide the user with the scientific data needed to accomplish the mission at hand. Okay, so we've talked about how ideally you only have the instruments on board that are like giving you the scientific data, but now we have to talk about what happens if something goes wrong. You need to have monitoring equipment. So let's talk about that. What am I trying to say here? Okay, I think I kind of summed it up quite well there. Oh, my window is slightly off, is it? There we go. There we go. Okay, so I've talked about why monitoring data is important. Next, let's talk about what we'll be using in this report to monitor the equipment we're looking to monitor. So that's the temperature monitor, the voltage monitor, and the switch monitor. Tree monitoring equipment. Use L2C. What's L2C? Or is that I2C? I2C. It's a good question. I imagine so. Arduino is super useful. Only thing is though, probably wouldn't be able to, like, if you have something made with Arduino in a satellite, let's say, and you have the controller on Earth, you won't be able to do anything because it's too far away. So you'd have to like pre-program everything completely so that it's like, let's say a cycle, I don't know, like if the solar array heats up, then start powering everything off the solar array instead of like your RTG or your battery, let's say. So you're basically using Arduino to be like, okay, we're now in daytime, use daytime controls instead of nighttime controls. Arduino could do that. I don't know if they do it, but Arduino could do it. There's probably some reliability issues as to why it isn't used, but it can be used 100%. Okay, so I need to say here, use list man for latex. Just 1 sec. What's up, boys? So what am I saying here? Okay, so first of all, I want to put in a picture of each component. So I'll do that by, I'll just, oh wait, I have it here already. So here, yeah, I want to have a picture of each component. I want to say what it's going to measure, and I want to say, oh, that's all I want to say, really, yeah. So like, I'll be like, oh, a temperature monitor will give back temperature. A voltage monitor will give back voltage, and a switch monitor will give information of as to if the switch is on or off. The reason why I have to do that is if you scroll down here to allocation of marks. Okay, yeah, so we say here why that part of the system needs to be monitored. So that's going to be talking about why do you monitor a battery? Why do you monitor a solar array? The second part is which of the approved monitoring components do you use? That'll be selecting which of those 3 components I pick, which is quite straightforward. Like, oh, for if I'm measuring temperature in a battery, I'll use a temperature monitor. That's that. And what output will that component provide? Instead of every single time I say I'm using a temperature monitor and then having to say what the temperature monitor gives out, I can just say in the introduction, temperature monitor, temperature. Voltage monitor, voltage. Switch monitor is a switch on or off. So that should be fine. Okay, so let's go back up here and do that. So probably best to use PowerPoint again for this. PowerPoint is great for formatting images. Like it's so good. I'll show you now. So what I'm trying to do is I would like I have 3 images. I want them side by side. So instead of having to wait. Over here. Oh, enter that. Okay, so yeah, instead of having to like use some like photo editing software, I can literally just paste each image here side by side, and then I can just do a snipping tool of the whole boy. So let's get this going. Okay, I have the temperature monitor, copy, and into PowerPoint, paste it. Just like this. Put that right over here. Next is the voltage monitor. So back over here, open this bad boy up. Voltage monitor, snipping tool, bang. Oh wait, no, the voltage monitor is up here. So I'm actually gonna have to, oh, this is very advanced. This is very advanced. I'm gonna have to do 4 pictures. I'm gonna have to do 1, 2, 3, and 4. And I'm gonna have to put this under that. This is gonna be tough, boys. Let's see. PowerPoint. What else am I up to? So I'm just gonna get everything here, and I can worry about kind of editing it around and making it look nice after. Okay. Nice. That's perfect. Oh, a little bit too high. All right, there we go. And then we just want to zoom in, so it's nice and kind of enhanced. Enhance that image. Perfect. And let's copy this. Snipping tool. And there we go. All you gotta do. PowerPoint, really nice for this. So I'm gonna save. Tree components. So I can put in the pictures later on. That's no issue. Have a quick cup of tea, boys. Okay, back in 10. Oh, Roy, what's up? You literally just got me as I'm about to take a break. Yeah. How are you, man? I'm back in 10 minutes, but yeah, if you gotta go, you gotta go, but back in 10. I'm just doing an assignment at the moment. I'll just quickly fill you in before I dip off. I'm taking a break from the thesis just because I have an assignment due on Friday. It's actually pretty fun. You're basically, I'll throw up the block diagram before I head off. Because this is the first slide, right? Here we go. So you got over. Maybe I should zoom out. There we go. This is like a spacecraft block diagram, and I'm basically in charge of making sure it's safe, making sure it can like survive and it's not going to break. And I have to do that by putting these monitors wherever I think it's important, and I have to talk about like my justification then in the report. Like why do I care about measuring the heat of the solar array, the heat of the battery? Why do I care about the voltage going through everything? So we're getting there. We have the diagram finished. I am pretty sure this is all I need to monitor. And then the next question is I have to actually justify why I'm putting stuff where I am. So it's pretty fun so far. It's kind of cool. But yeah, back in 10. Phew. Ah, I'm back. I was just saying that I want to watch a video when I have my cup of tea. And I was not too sure what video. Do I want to watch A Better Planet Than Earth Ever Discovered in Galaxy? Or do I want to watch What If We Placed 8 Billion People on Mars Now? And I think I want to watch What If We Placed 8 Billion People on Mars Now. That's pretty wacky to me. So let's jump over. Okay.
Moving is like experiencing a fire, flood, and being robbed all at the same time. Moving is and I'm like merely experiencing about changing apartments or houses. But what if I say that one day we'll have to move to another planet? For example, to Mars. In truth, this is
I can't watch Expanse clips. What if someone hasn't seen it yet?
Happening on Earth. You've probably heard that the population of our planet is growing faster than nature can produce what we need. Currently, the population of the Earth is about 7.8 billion people. According to scientists, by the year 2057, it will already be 10 billion, and by 2100, almost 11. Have you ever lived in the same apartment or house with 20 or 30 relatives? A similar situation will soon happen on Earth. It's time to think about inhabiting a neighboring planet. For example, Mars. Not Neptune, it's too far away. I must tell you that the number of people inhabiting Earth isn't the only reason to pack our things, jump into a rocket, and rush to another planet. Yes, there are many of us. And yes, there aren't enough resources for everyone. But while we somehow are learning to survive in these conditions and doing it well, what if an asteroid crashed into the Earth? When scientists determine that collisions are unavoidable, we'll have...
The asteroid point is what I say to a lot of people when they say to me, oh, what's the fucking point in doing anything to do with space? Like, we should look after our own planet first. Overpopulation is something that's like, I think about quite a lot. I just never bring it up whenever I say to people, whenever I try to answer that question. So yeah, I like those 2 points. If an asteroid hits is a big one. By splitting population between 2 planets, you essentially reduce your chance of extinction to 0. And the second point is overpopulation. We're getting too big. We want to kind of send people to different places, make resources in other places, whatever. One of the solutions to the Fermi paradox is asteroid hits. What's the Fermi paradox again? Heard of that? Fermi paradox. The contradiction between the lack of evidence for... Oh, yes. So we don't have evidence of aliens, but there's a very high chance there is aliens. So the paradox is, if there's a high chance of there being aliens, you would think that we would have evidence of aliens being there now. Is that what it's about? Does that make sense? Yeah, and the paradox is that we actually haven't seen anything yet. Oh, so when you're saying one of the solutions to the paradox is blah, you're saying that like the reason we haven't seen anything yet is because asteroids probably not.
No other choice. We'll have to run.
That makes sense.
But there's one problem. Okay, not one, but one key problem. In diameter, Mars is half the size of Earth. More precisely, its radius is 53% the radius of our planet. If we compare surface areas, then it doesn't look so bad.
Oh yeah, so... Wait, my camera does what? Pretty dark. Oh, I think it's because the sun's probably going out, whatever. Really interesting about Mars, right? So it's half the size of Earth, like in terms of radius, but because Earth is like 73% water or whatever, I don't know what the number is, but it's more than 70. There's actually more surface area on Mars than there is on Earth. That like people, you know, with land you can chill on. So that's fucking crazy to me, I think.
The surface area of Mars is 144.37 million square kilometers. That's 55.74 million square miles, which is only 28% that of the Earth. But if we take all the Earth's land into account, excluding the ocean, then its surface area is close to that of Mars. But add here that Mars's mass is only 642 sextillion.
That's interesting, you know? Like, okay, if you think about it, the surface area of land on Earth is roughly the same as Mars. So if you were to have a lot of people on Mars, like the travel distances would be insane. Like, you know, it'd be as if like you have like, let's say, the Atlantic Ocean, but like you can have like cities there, you know? That's why it's pretty sick to have that many people on Mars, because like there's much more space to utilize. Whereas on Earth, like you can't really have like a city in the water. I mean, you can, but it's not really ideal, right? Why we don't do it.
Killion kilograms. That's 1,415 sextillion pounds, which is 10 times less than the mass of the Earth. Now, these aren't just dry numbers from a textbook. A planet's mass directly influences our ability to survive on it, because mass affects the force of gravity. The longer you live on Mars, the more problems you'll have in your muscles and spine. We're used to completely different loads. And yet, this still isn't the main problem. Perhaps people are concerned about the overpopulation.
Okay, let's be real. The reason Venus works is because, yeah, it's in the water, but I mean, like, you can just go on the land straight away, right? I mean, like, if you go outside the gates of Venus, or not Venus, Jesus, of Venice, you're on the road, right? Whereas, like, if you have a city like right in the middle of the ocean, when you leave that city, you're still going to be in the ocean. So it's very hard for like supplies to get there, supplies to go out, for electricity to be supplied, imports, exports. I don't know. It's just not really functional, I would say.
Of Earth. Well, this problem would be especially more intense on Mars. Where would we all fit? To start, it's worth noting that we wouldn't all immediately fly there in full force. First, a small group would go, for reconnaissance, so to speak. These pioneers would have to prepare everything for the arrival of the main group, which we likely could end up in. The first thing a group of scouts would have to do is set up agriculture. There's absolutely nothing to collect on Mars, so you could forget about hiking the forest for mushrooms and berries. Everything would have to be grown by ourselves. But there's something to rejoice in. According to scientists, under certain conditions, beans, potatoes, and asparagus could take root on Mars, so we wouldn't stay hungry. However, you would have to bring along a stock of products with a long shelf life. You'd need to eat something while waiting for the harvest, and that's no quick matter. So, while you're waiting for the first sprouts, you could start the construction of houses. But what would we build from, you ask? Carrying equipment and building materials would...
I still think the way forward for terraforming Mars is to live below the surface. Because even if you have all these gas like on Mars, you're fucked from the amount of ultraviolet light that's going to hit you. There's no atmosphere, so like you're absolutely screwed. I mean, when we wear like sun cream and stuff, I'm pretty sure that that's battling the 1% of UV light that gets in the atmosphere onto Earth. You have 100% of that UV light hitting you. Okay, maybe there's a little bit less flux because of the distance away from the sun it is compared to Earth. But you can fucking bet your bottom dollar it's like double, if not triple the amount that Earth would be getting. Sorry, what am I saying? Way more. Like 1%, you know? I don't know. I think it's all about the tunnels in Mars. Also, that's where the water is as well. So if you had like underground bases with like around the lakes of water, I think that's the way to go.
Would be very expensive. Therefore, scientists are looking for other options. One is 3D printers, but their ink also isn't cheap. So scientists have proposed replacing this with the material which is most abundant on Mars, dust. This would significantly...
Ooh, I haven't heard of this before. Interesting.
And reduce costs. Thus, construction technology and the selection of materials are solvable problems. But where would all those people who'd build the houses from Martian dust live? At NASA, they're already dealing with this issue. In 2016, several companies began developing prototypes for designs that could be brought to Mars. The list of requirements for them is huge, which, in general, isn't surprising. It includes protection against ionizing radiation and the ability to maintain comfortable living.
That looks sick. Holy shit, look at that. If you saw that, like that's gonna be in like fucking housing magazines. Oh my god.
Among a whole lot more. Of course, people still have no experience with life on other planets, but the developers are relying on the principles of the life support systems already operating on space stations. Except perhaps their tight quarters. Proportions are much smaller there. Everyone needs their own personal space. Let's hope that in the permanent homes for life on Mars, this would be accounted for. So, preparations for the relocation to the Red Planet are in full swing. NASA even has mining covered. For this, they've created a special robot called Razor. In the big picture, it looks like their progress is moving in the right direction. They're giving attention to the smallest details and searching for solutions to potential problems. But some questions regarding life on the Red Planet don't have answers. For example, how would we deal with Mars's atmosphere? You can't stay in the closed confinements of a space station. Before you go out for a walk on Mars, remember that about 95% of the planet's atmosphere is carbon dioxide. This means you couldn't go outside without pressurized spacesuits and oxygen tanks. Mars also doesn't have a global magnetic field comparable to Earth's geomagnetic field. Combined with a thin atmosphere, this means that a significant amount of ionizing radiation reaches its surface. In other words, you need reliable protection for your whole body if moving to Mars is on your to-do list. In addition, in the harsh Martian conditions, there's an extremely unpleasant phenomenon for all humans. All the water that reaches the Red Planet begins boiling at 4 degrees Celsius or 39.2 Fahrenheit. So the first settlers of Mars, alas, couldn't do without a spacesuit. And the problems don't end there. The temperature on the Red Planet varies greatly. At the poles, it's in the minus 153 degrees Celsius area. That's around minus 243 Fahrenheit. In the daytime, half of the air warms up to 20 degrees Celsius or about 68 Fahrenheit. And at the equator, even up to 27 degrees Celsius.
Yeah, I'm pretty sure it's to do with the pressure. Just the way pressure and temperature works on Mars. I think lower the pressure at that temperature is like insane number compared to what it would be on Earth. So that's what accounts for the low boiling point.
Celsius, or about 81 degrees Fahrenheit. So you think you can easily stand?
I actually didn't know that either, to be honest.
Mars would quickly convince you otherwise. If you want more comparisons of the Red Planet with ours, here's an important fact for you. Mars revolves around the sun more slowly than Earth. So 1 year there takes 669 Martian days, or 687 Earth days.
I mean, surely with a spacesuit, the impact is that you just boil, right? Yeah, your blood just boil. That's what I was thinking.
Seasons are similar, however, they last longer than 3 months. But let's get back to the main question we all gathered here for. How would we all fit on Mars? First, let's calculate how many of us there would be. Not everyone could fly. To go to space, you need to go through some tough training. So if you have health problems, you may not be allowed into space. But imagine we solve this problem somehow. For example, as in the film Passengers, everyone could go to bed in special capsules with full life support. Another problem is that many travelers drop out during the flight. Out of the 45 spacecraft sent to Mars since the 1960s, in 26 cases, something went wrong. Therefore, the risk of flight failure is really serious. Taking off can also lead to a disaster. But even still, there may not be enough space on Mars, so what could we do? Unfortunately, scientists still don't have an answer. One suggestion is to create underground dwellings. By building a series of tunnels,
that would be my idea.
Underground habitats, colonists could abandon oxygen tanks and pressurized suits well away from home, so all is not lost. It's possible that you could be among those who first moved to Mars. Despite the many difficulties that await migrants, people talk about moving to Mars. For example, Elon Musk, who was going to colonize the Red Planet and turn Earthlings into a multi-planetary civilization. This was one of the key goals of creating SpaceX. Over time, many of the problems facing life on Mars could still be overcome through the use of geoengineering, or rather terraforming. Using organisms like cyanobacteria and phytoplankton, colonists could gradually convert most of the carbon dioxide in the atmosphere into breathable oxygen. It's also possible that we could use orbital mirrors to heat the surface and bombard the red planet with comets. Regardless,
Orbital mirrors, that's in The Expanse, I'm pretty sure, over Ganymede. Like, yeah, that's literally just to make it so it's warmer, so people can chill there a bit easier. You don't have to put as much resources into heating like the buildings you're in.
Of the method, all existing options for terraforming Mars could make it inhabitable for humans in the long term. If you like this video,
Pretty good. I really like this channel. Definitely check him out. I think it's just called Riddle. Yeah, it's a big like for me, my pal. All right. Okay, so I have to end the stream in like an hour. We have a viewing happening, and I have to clear out when they come in. Space Doc, let me check it out. I'm always looking for more kind of spacey channels to watch during my breaks. Oh, is this the channel that you showed me with the spaceships in The Expanse and like how they're not really designed to battle that well? Okay. I'm actually not gonna, if there's spoilers I won't bother. But that's a cool idea. I like that. Because like, there's really interesting spaceships in sci-fi, you know? I'm really loving watching The Expanse and like seeing how things have progressed, you know? Like I just watched the episode this morning when Draper goes to Earth. And like they do it really well where it's like she's like really excited to go and like the preparations she must take to like experience 1G. I think it's pretty cool, you know? Like they're always wondering like what the ocean's like. Same in Attack on Titan too, I guess. Okay, so as I was saying, I have like an hour before I have to dip off, so I wouldn't mind getting a bit more of my coursework done. So where am I at the moment? Okay, so I was just about to speak about each monitor and what it does. So I'm just gonna do it in words now, but I have to come back at some point and use the latex command to like do a list. It doesn't take that long. Fuck it, let's do it now, will I? I probably have it here, do I? Table. Okay, I have table. I have image. Nah, okay, I'll do it later on. Just because I probably have the command in another file. But I just don't want to be going around to different files right now. I just kind of want to get some work done. Okay, so one, the temperature monitor. So the temperature monitor literally returns the temperature of the component that the monitor is fixed to, or is applied to, I guess, because it's not necessarily fixed. If you can always change it around, but obviously you can't change it around when it's in space unless you have like, I don't know, some sort of fucking crazy remote control thermometer that can move around. Two, the voltage monitor. And this returns the voltage across the component that the monitor is applied. Voltage drop, I guess, might be more correct to say. And then finally we have the switch monitor. And oh, I need to change my scene as well, actually, don't I? Yeah, I do. Hold on a sec. Okay, cool. Oh, I'm not liking the camera. Like, oh, what if I go at this? Oh, the sun's going down. Thank God. Okay, what am I up to? Switch monitor. Returns a binary figure to inform the user if the switch is turned on or off. Okay. Now, I think that's all I want to say in the introduction, to be honest, and I might just move on now, and if I feel like I need to come back and add more words to it, I can always do it later on. Let's just quickly skim through what I've said here. Okay, in a spacecraft, you have scientific data and you have housekeeping data. Ideally, you would have as much scientific data as possible. Ideally, in a perfect world, you'd have 100% scientific data. But unfortunately, things go wrong, and you need monitoring information too, to make sure that before something breaks, you can intervene and make it so it keeps on working. It's like a constant battle between scientists and engineers, where the scientist is like, okay, let's just get as much data as we can about what we're looking into. The engineer then would be like, okay, you can do that, but like, how long do you want your mission to last for? You know, if it's a mission that requires, like, let's say 5 years of data, yeah, cool, you blitz away, but if you don't have this monitoring data, your mission might last 2 weeks. So this is achieved by monitoring the temperature of a battery, let's say, or your shunt regulator. Then making sure, well, this is kind of outside the scope of this report, but if you were talking about the design of it, you'd make sure that the battery and the shunt regulator would be like at 2 separate parts of the spacecraft, so that excess heat coming off either of them won't affect the other one. So that's more of like the kind of the battle between engineers and scientists about what's important and what's not important, I guess. So yeah, just saying here that you achieve this through having monitoring equipment, and as opposed to waiting for something to break and then knowing it's broken, the monitoring data instead kind of gives you advanced warning as to something is about to break, and that's typically through how hot it gets, especially for things like the solar arrays or things like the batteries, let's say. And then with that information, you can decide to, like, oh, turn this off, redirect the power here, dissipate more power here instead. It's sort of like a traffic system, right? Like, if you have loads of traffic in a city going like down one road, wouldn't it be cool to divert some of that traffic down another road that will lead to the same place? That's essentially what's happening here. It's like you have like a huge traffic jam, and what the monitoring data does for you is it gives you advanced warning of like a big jam happening that like clogs up the whole road. And if that clog gets so bad, it might end up like sacking off like a really important busy road like way back. So ideally you get advanced warning of that happening, and then you're able to divert the traffic down different roads. It's kind of what's happening here, except instead of traffic and cars, it's power and electricity. Okay. So yeah, let's just go on to the next section. I'm not too sure how I want to format this, so I have a small think. I think I might go through it like component by component, say what I'm measuring, say what it'll return, and justify why I'm putting that into place for each individual one. I think that's probably the play here. I think I could probably put more information into my monitors. So if we check the PowerPoint here, the second one, I could probably discuss like what's happening in each individual one. So yeah, voltage monitor measures voltage, but like why is this diagram the way it is? I can probably include that there as well. And that's probably important actually to do. So I might actually do that now. Because if I'm doing it all in one place, I think it's important to do that. So a thermistor is like, it's like a resistor that instead of changing with electricity, it changes with temperature. Which varies its resistance as temperature changes. This change in resistance alters the voltage running through the component, and this can then be converted to a temperature value. Okay. That's actually pretty important. So like I was wondering, what's the point of a switch monitor? But like it's sort of like kind of positive feedback, right? It's like if you have your phone out and you're like texting and like you press a button and like it vibrates a bit, it's like that's good. We like to have feedback that what we're doing is working. Similar to if you press the button of an elevator, you're probably going to be happy if like you see the button light up or something, or if you hear the elevator coming. But imagine you press the button and nothing happens. Like you get a bit anxious. Let's say you're like, oh, what the fuck? Did I press it? Is it working? So this sort of monitor is actually important just to make sure what you've done actually took place. I wonder how many references I need to put actually in it. Okay. So let's talk about maybe the solar array first. Let's go left to right. Oh no, actually they gave us we check here. Okay, yeah. So number 1 is the solar array. Excuse me. Nice way to get some word count here. Just all 3 monitors, namely temperature monitor, voltage monitor, and switch monitor need to be used. I wonder what my word count is actually at the moment. Let's do a quick check. So, oh, I have nothing here yet. I reckon I'm at like maybe 500. Not bad. Pretty close. Oh, I didn't actually... Oh, I might be okay. No, I say I'm like 480. Oh! Oh, baby. 480, baby. It's gonna go to the bathroom. My issue here is that I don't really know. How do I say this? So I know it's important to monitor the solar array, but I don't know how to justify, like, have a different justification for temperature versus voltage, let's say. Yeah. But anyway, boys, I have there's like a house viewing happening soon in my gaff, so I have to clear out. I have to dip. But yeah, thanks for hanging out. Thanks for watching. I'm happy I did this today instead of my thesis, just because like this is due very soon. So like have it like I think I got what 600 words done, and the whole report's 3,000 words. So yeah, trucking along. Happy out. Yeah, thanks for hanging out, boys, and have a nice rest of your week, and I'll catch you soon. I won't be streaming anymore this week, unfortunately. I'm moving house on Thursday, so tomorrow there's cleaners coming in, and they'll be cleaning during the normal stream slot, and on Thursday that's when I'm actually moving.